let's get started. Welcome back. Hope you had a good 3-day weekend. So I want to start by going over the class website. I made some changes. Notably, homework 1 was pushed back a little bit, but homework 2 is not pushed back too much. The reason for this is I realized we're taking things a little bit more thoroughly, which is great. But because of that, I know at the end of last class I promised that we'd cover more of regularization. We'll come back to that later. I want to cover what's needed for homework 1 first, just so you can get to homework 1. And by the time we're done covering what's needed for homework 1, we'll also have basically covered what's needed for homework 2 as well. So you could kind of start both concurrently. We'll post the new homeworks after that based on how far we get in the class, but they'll all be assigned at some point. Just exactly when will be based on when we cover it. Okay, so we will come back to regularization. That's not needed till homework 3, so I figured there's a lot more to cover there, but probably best to cover what's needed for the homework. Okay, so to review where we left off last class, we learned about our first regression model called linear regression. This is all just review, where the goal of linear regression is given data to find the line of best fit. So something like that, where the points are the data and the line is what's learned. So we went one level deeper. How? Well, we said that we'll learn the model parameters, theta, which minimize the notion of square error. Okay, so how? We went one level deeper. And we defined loss functions, and so we wanted to find the parameters theta, which specifically minimize the mean squared error loss, which was the loss function that we defined. And more specifically, we came up with this equation where we found the minimum value of the parameters that minimize the average. And we talked about how this notation is average, where you sum up all the data points, divide by the number of data points, that's average, of the true values minus the predicted values squared, where the predicted value could also be written as mx plus b, but when that's expanded out to multiple variables, it looks something like this. And this is equivalent to, and I'm going to write it in this way because this will be useful when we're talking about other models, to finding the parameters theta that minimize the average of the distance. So conceptually, we could just think of this as the distance between y sub I and y hat sub I, where y hat sub I is again this. And where the distance function we happen to have chosen for various reasons is the mean squared error loss. We talked about some of those intuitive reasons last time. Then we started talking about regularization. We will come back to that, but for now we'll just say, how do we find this minimum parameter value? And we will cover that later. But for now, the level of depth that we've gone to is that we have this notion of error, the distance between what our model should have predicted and what it actually predicted. And we want to find the parameters that will minimize that error, or minimize the distance between what was predicted and what should have been predicted. So any questions on this high-level overview from last class?
So, yeah, you're trying to find the minimum theta for this function.
Mm-hmm.
The sum. Where is the minimum theta? Where's the theta in this?
So y hat sub I expands to this theta 0 plus theta 1 x1 plus dot dot dot.
Okay.
So you want to find the minimum. So when I just write theta, that means the set of individual theta values.
Okay, so y hat expands to
Yeah.
that. Thank you.
That's what that small squiggly arrow is. But maybe that should be a different color. I've been posting these notes. Oh, we're still out there. I've been posting these notes online, so you could just look at the notes. Let me maybe so it's easier.
I'm just typing them up for myself.
Okay. Any other questions? Okay, so that's our first regression model. We talked a little last time about how you could expand that into more complex forms of regression. But for now, I want to talk about how this idea expands to do classification. So now we will talk about our first classification model, which is confusingly, for historical reasons.
Wait, can you scroll down up a little bit? Yes.
Sure.
Okay.
Yeah, I'll keep it here. Which is confusingly, for historical reasons, called logistic regression, but it's not used for regression, it's used for classification. And so to understand logistic regression, we need to talk a little bit about how we model binary classification problems. So we're going to start just talking about the binary case for today. That's all you need for your homework. So when I say binary predictions, that's predicting between one outcome and the other, cancer versus no cancer, etc. So for these binary classification problems in general in machine learning, not just for logistic regression, let's write that out. For binary classification, we output the probability that the class equals 1. And when we say class in classification, let's define that. So class is the different things you can predict in classification problems. So a very useful function that we're going to learn about and which we'll see repeatedly in this class is called the sigmoid function. And first, let me just define what it is, and we'll go into the intuition just for today about why it's useful. So the sigmoid function looks like this. I'm going to draw y equals 0 here, y equals 0.5 over here, and y equals 1 here. This is not the function. These are just dotted lines to make it easier to draw the function. So the sigmoid function looks like this. Kind of goes out. It approaches 1 as x goes towards infinity and approaches 0 as x approaches towards negative infinity. the equation for a sigmoid function, so we'll just call this sigmoid of x, or for short, we'll just say s of x, has the following form: 1 over 1 plus e to the negative x, or another way that this is written is e to the x, eraser, e to the x over e to the x plus 1. These are the same thing, just with algebra. People like to write it in different ways. So there's some pretty useful properties of the sigmoid function that make it an appealing function to use for logistic regression and for classification. So properties, well, not just properties, useful properties of the sigmoid function are, number one, that the output of the function is between 0 and 1, i.e., it is a probability, or it can be interpreted as a probability. So that's pretty useful if we're predicting probabilities. Second useful property is that the confidence of increases, and when I say confidence, I just mean the probability. We'll talk about what this means more in a bit. So the confidence, aka the probability, increases more quickly near the middle so like when x is near 0, and more slowly when it's away from the middle. Okay, so far we've just talked about the sigmoid function and really haven't connected it back to classification yet. So let's do that now. So what we do in logistic regression is combine the ideas of linear regression with the sigmoid function. So in logistic regression, what we do is learn, I'm going to go back to the M and B notation just to mix it up a little. So learn optimal parameters, i.e. M's and B, for the function y equals the sigmoid function of mx plus b. In other words, instead of doing y equals mx plus b like we do in linear regression, we do y equals the sigmoid function of mx plus b, which, just plugging that in, expands out to 1 over 1 plus e to the negative, notice here 1 over 1 plus e to the negative x, but instead of e to the negative x, it's e to the negative mx plus B. And just to write this more generally, so, or more generally, we can say y equals S of, we could go back to this other notation with multiple variables.
So it's really e to the negative to the minus e to the minus mx minus b.
Yes, yeah. Equals, but it's useful to write it in this form for conceptual reasons, which we'll get to. 1/1 plus e to the negative theta 0 plus theta 1 x1 plus ... plus theta n x. And try to get that parentheses in here. Y'all know what I mean. It gets kind of messy at the end there. Okay, cool. So this is interesting because we're now doing regression. We're learning the weights of a model to make predictions, but those predictions are all going to fall between 0 and 1, i.e. a probability. So if our true data are zeros and ones, the things we're trying to predict, and our input data is the same as before, a bunch of x1s, x2s, x3s, if we train a model using the same methods as before, we will now get predictions that are between 0 and 1. So let me just write the optimization goal again, and then I'll take questions. So the optimization goal, written in a similar way to how we wrote linear regression, goal is to find the minimum value of the theta parameters, again, of the average of all the data points, of the distance between the true value and the predicted value. So this is actually exactly the same as linear regression. We're doing the same thing when we write it like this. But now, to put in what we learned about this sigmoid function, so I'm just writing out the same exact equation. And today we're not going to talk about what distance measure is good for logistic regression. We'll cover that in a near future class. The distance between the true value and the predicted value, where the predicted value is not theta 0 plus theta 1 x1 plus ... plus theta n xn, but sigmoid function of theta 0 plus theta 1 xn plus ... plus theta n xn. So 1 plus e to the negative theta 0 plus theta 1 x1 plus ... plus theta n xn. And just to emphasize, both the true value, so the true value has two forms. It can be 0 or 1. So that's what our ground truth data looks like that we're training on. And the predicted number is going to be between 0 and 1. Okay, let me pause and take questions. Starting here.
Is there any other functions besides the sigmoid that is used? I mean, there are so many functions that fit between 0 and 1.
Yeah, so there's a ton of functions that can get you between, take a linear equation and collapse it between 0 and 1. Sigmoid has many nice properties, including these two the second property here, where if you're predicting values that get closer to infinity, the probability increases really slowly. It converges to 1. Whereas if you're really not confident the confidence, where confidence here is how much greater are you than 0.5? Because if you predict 0.5, you don't really know whether the true value is 1 or 0. As you get further away from 0, or the mx plus b stuff coming out, evaluating to 0, the confidence quickly increases and then slowly decreases. So it has that nice intuitive property. There's other mathematical reasons why it's nice, which we will get to soon, once we learn about how these models are optimized, and once we answer the question in a future lecture of this final how, of how do we actually find these minimum theta values, which we're not at yet, and which you don't need for homework 1 or 2. But once we do cover that, it'll make more sense to give more reasons as to why we really like the sigmoid function, as well as other things like why we use regularization. I think coming back to regularization after that will help as well. Any other questions? Sure.
Yeah. So basically for question 2, we're given
We didn't cover enough for question 2 yet.
oh, okay, I'm sorry, I thought we moved.
The goal for this week, possibly by the end of today, but definitely by the end of this week, will be for everyone to be able to answer question 2 and 3 on the homework. You could already do question 1. Question 4, if you know Python, you'll also be able to answer that by the end of this week. If you don't, then we'll do a Python refresher and cover NumPy and all those libraries. And after next Tuesday, you should be able to answer every question. So either by the end of this week, if you already know Python, otherwise after Tuesday. And then hopefully that's enough time to answer, do homework 1 and 2. Homework 2 is just a little bit delayed because there's this nice extra credit portion to it where if you're in the top 15 submissions, you get extra credit, which is kind of cool. Any other questions? Yes?
So is logistic regression just a probability function?
Yeah, you're learning to predict probabilities. Probabilities of a binary outcome, that you're 0 or 1, that you're no cancer or cancer, for example. Yeah.
So if it wasn't a binary output, but it was still a countable number of outputs, would we scale the sigmoid function, or would we create a different probability distribution?
We'll get to that later. There's this thing called the softmax function, which is used for multi-class classification. We'll get there, but not for today, just binary. We don't want to complicate things too much. Yeah.
But I guess to kind of build up on his question, like, why does it have to be a sigmoid? Why not a Gaussian, for instance? A Gaussian is also mathematically easy, right?
Yeah, we'll get to that. There's this generalized. Yeah, we'll cover that soon.
I'm a little confused with those theta for the second minimum function. So you have the actual value and you have this this y hat is basically equal to that thing.
Mm-hmm.
Okay, so that is the y hat.
Yeah, this is just the expanded version of y hat. From this equation here. What we're predicting is sigmoid function of the linear equation. And for that reason, logistic regression is considered a linear model. To see this graphically, let's look at an example of why logistic regression, and this might help with the intuition some more, why logistic regression learns linear decision boundaries. So let's go back to our pictures and look at a data set where we have 2 input variables, x1 and x2, and the data are separated like so. Actually, for this, I have to draw it really precisely so that it's easier to. Okay, that's not really precisely, but that's precisely enough, I guess. So 3, 2, 1. So we have one class of data points in the blue class and another class of data points up here in the red class. And so the learned model in logistic regression, let's say we train a logistic regression model. We do this finding the minimum parameter values, which again, we're not covering how that happens, but we do the machine learning process and we find those parameter values, and our learned model ends up being the following, where, and actually let me make this really clear. Let's say the learned model is, okay, y equals the sigmoid function of theta 0 plus theta 1 x1 plus theta 2 x2. This is logistic regression, what with just two variables. And let's say that the learned parameters are, so I'm starting to write this in vector notation. Don't worry too much about what that is, but basically the learned parameters are -3, 1, and 1. So we did the machine learning process. In other words, we did that last how, though we haven't talked about how that works yet. And when we do that, what we're essentially saying, let's draw the sigmoid function again to explain this. So I'm drawing the sigmoid function again. Let me do it less precisely to be a little quicker. So we have that sigmoid function, 0.5 and 1, where the x here, remember the sigmoid function is sigmoid of x. So the x here in the input to the sigmoid function is the linear equation theta 0 plus theta 1 x1 plus theta 2 x2. That's the input to the sigmoid function. And the output to the sigmoid function is the logistic regression equation, or sigmoid of theta 0 plus theta 1 x1 plus theta 2 x2. And again, just to redraw that sigmoid function, it looks like that, where over here we have x equals 0. So what this is saying is that we are predicting, let's see if I can draw it in this little box. So this is the same thing as saying predict, or let's say that, actually I don't think there's enough room to put it in this box. Does everyone have this top part written down? Okay, I mean, the notes are online anyways. So this is the equivalent of saying, if we assume that our decision boundary is 0.5, so if decision boundary equals 0.5, so new vocab word, so i.e. predict 1 if the predicted probability is greater than or equal to 0.5, and otherwise predict 0. So that's what a decision boundary is. So if that's our decision boundary, then another way to write this is predict 1 if -3 because these are the learned values, -3, 1, and 1. So if -3 plus 1 times, oops, not theta, 1 times x1 plus 1 times, that's a 1, 1 times x2 is greater than or equal to 0, and the reason is because, remember, the x-axis is theta 0 plus theta 1 x1 plus theta 2 x2. So if when that whole linear equation is above 0, we start getting values above 0.5 in the sigmoid equation. So because we're writing it like this, another way to write this is just using some algebra, that x1 plus x2 equals 3 is the decision boundary. So we just rewrote, did some algebra, put the -3 onto the other side. So if we draw this line, x1 plus x2 equals 3, on the plot up here, let's draw that, maybe in this color.
Can I ask a quick question?
Sure.
Scroll down to a little bit. Why is the function greater than or equal to 0 instead of 0.5?
Because it's the x-axis. So the x-axis is theta 0 plus theta 1 x1 plus theta 2 x2. So that's what we have on the left-hand side of that inequality. Theta 0 plus theta 1 x1 plus theta 2 x2. When that's greater than or equal to 0, so when the x-axis of this plot is greater than or equal to 0, the y-axis is greater than or equal to 0.5. And since we predict 1 whenever the y-axis is above 0.5, we're predicting 1 whenever -3 plus x1 plus x2 is greater than or equal to 0. Okay, let's slow down a little on this. So, let me put
I
it.
think I had the same question where it's asking, like, instead of doing -3 plus 1 x1 plus x2
Mhm.
equals 0, why wouldn't you set it equal to 0.5?
Right. So yeah, so it's the axes. So this is, let's look at this. So this, another way to write this is theta 0 plus theta 1 x1 plus theta 2 x2. That's the x-axis. So over here is theta 0 plus theta 1 x1 plus theta 2 x2 equals 0, right? And the corresponding y value, or the prediction, is 0.5. So we only predict 1 when this x is greater than or equal to 0. Because 1, the y-axis is the prediction. If we're predicting 1 whenever the prediction is greater than 0.5 probability, which intuitively makes sense, then we would then we write it in this way. So this 0 is the x-axis in the sigmoid plot above. Any other questions about that? Okay.
Is it when you predict 1 when it's the greater or equal to the threshold?
Mhm. Yeah, I mean, you could say greater than the threshold and less than or equal to predict
So
0.
If it's exactly the threshold, what do you do?
You can define your threshold to be greater than or equal to 0.5 or greater than 0.5.
So in the homework, it says 0, 0.2, 0.4, 0.6,
Yeah.
etc. So does that mean are you using a greater than or equal or less than or equal?
It won't make a difference for the homework.
Okay.
But we're not yet at the homework.
I'm just wondering, sorry.
No, great question. Okay, so let's draw this decision boundary. So x1 plus x2 equals 3.
I have
Yes, great question. That is something that someone chooses, the ML engineer chooses. 0.5 is a nice intuitive default because you flip a coin. If it's greater probability than flipping a coin, you might as well predict the 1 versus if it's less probability than random chance, you
But then
predict
that's
0.
for 2 outcomes. What
That's
if-
only for 2 outcomes.
So this is binary.
Yeah, today's just binary. We'll get to multi-class later. Multi-class is the same idea, it just generalizes a little bit. So a great point. So this 0.5 is set by in last class we had that lambda parameter, which is also, so you'll see that there's a lot of hyperparameters that are set by the ML engineer, i.e. yourselves. We don't say parameter because, again, parameters are these theta. That's what's learned by the model. So we say hyperparameter because the model doesn't learn that. You said it. Yeah.
The -3 and 1 and 1.
So that's just from up here. Let's say you did this machine learning process and it spit out those coefficients. That's what the model ended up learning. We haven't learned how that happens yet, but we will very soon. But it's not needed for homework 1. Homework 1's all about, once you have a model, how do you evaluate that model? Okay, so let's draw this decision boundary. Okay, so x1 plus x2 equals 3 gives us that line. And so now, just intuitively, based on this equation, if we have a point where x1 where x1 comma x2 as a coordinate is above that line, it will predict the red class. If it's below that line, it'll predict the blue class. So just intuitively, that's why we say logistic regression is a linear model, because it learns these linear decision boundaries. Just one final comment. We could easily extend this idea to nonlinear decision boundaries. So let's just see a quick example of that. Example of a non-linear decision boundary. And we're going to do the same thing here. Let's say that we have our data. So again, we have x1 and x2. But now our data can't be separated by a line. We'll go quickly on this concept because you don't need it for homework 1. But it's kind of cool to see as a sneak peek for the rest of the class. So you have the red and blue that are separated like so. So logistic regression's not going to work here. But what we can do is, let's say we have a more parameterized model. So our learned model is instead y equals sigmoid of theta 0 plus theta 1 x1 plus theta 2 x2. So that's same as logistic regression from before, plus theta 3 x1 squared plus theta 4 x2 squared. And let's say the model ends up learning the following parameter set. So we'll make this simple and say that it learns the following. So using the same logic as above, now it changes to predict y equals 1 if -1 plus x1 squared plus x2 squared is greater than or equal to 0, which means that x1 squared plus x2 squared equals 1 is the decision boundary. And flashback to geometry, I think. I don't remember this from geometry, but it turns out that's the equation of a circle. And this is the equation for x1 squared plus x2 squared equals 1. Who remembers that from geometry? Oh, okay, nice. I didn't remember that, but that's until I did machine learning again. Cool. So that's how you could extend this to beyond linear decision boundaries, but this is no longer logistic regression because you don't have a linear equation within the sigmoid function. Okay, so we'll cover more details about logistic regression later, including notably what we left out is what is this distance metric? It's not going to be mean squared error like it was for linear regression, but we're not going to cover that today. So I want to switch now to the new topic of evaluating machine learning models. So in your homework 1, questions 2 and 3 deal with a logistic regression model, so hopefully it's clear what that model is now. And in those questions, as well as the coding in question 4, you're evaluating the model in different ways. So evaluating supervised ML. So for regression, this is actually really easy because MSE satisfies the properties of a good loss function, which we'll talk more about later. So, but it does satisfy those properties, and it's interpretable. So, and it's interpretable. Sometimes people like to use something called root mean squared error, which is the square root of the mean squared error, which converts it back into the original units of your data. So sometimes people prefer this so that you have the original data units. But in summary, for regression, your loss function and what you use to evaluate your model on a separate held out data set, which we'll talk about in a bit, are the same. In classification, however, we didn't talk about the loss function, but it's kind of hard to interpret, and we'll talk about that loss function later. So instead, we use human interpretable classification metrics. And to visualize what these metrics are, I mean, we've all probably heard of accuracy, right? Like, what's the accuracy of a model? So accuracy's good, but there's some issues with accuracy. So let's get a fuller picture of what happens in a classification model. Homework 2 is on a classification model. So when you're doing classification, your model is going to make predictions, and you have two sets of data in binary. You have the situation where the true value is 1 and you have the situation where the true value is 0. So what I'm going to draw here is a circle inside of the square, which means that the model predicted a positive class, aka 1. So a circle means the model predicted a positive, new vocabulary word, class, i.e. 1. Or you could have, right, sorry, not a 1. For the 1, I'm going to draw an X, which is, I'm realizing, kind of confusing because sorry. I just want to make sure sorry, erase all that. My bad. So 0 means that the true value is positive rather than the predicted value. So I'm just rewriting everything, I guess. i.e. y equals 1. And when I draw an X, that means the true value is negative, i.e. the y true value is 0. So I'm just going to draw. These are just data points in a Venn diagram. This is a Venn diagram, by the way. It's not a plot of anything. Let me clarify that. So Venn diagram type of thing. And inside of the circle, we're drawing points where the model predicted the positive case. And outside the circle, we're drawing cases where the model predicted the negative option. Okay, so looking at this Venn diagram, inside of the circle are all the points where the model predicted positive. So in here we have the true positives. So those are the cases where the true value is positive or 1, and the model predicted the positive class or 1. So TP equals true positive. We also have, on the other side of the circle, false positives. So these are situations where the model predicted the positive class, but it's not the positive class in actuality. We also have false negatives. So false negative, where the true value was positive, but the model predicted it to be negative. And then we have true negatives. True negative, where the actual value is 0 and the model predicted it to be 0. So these are 4 new vocabulary words: true positive, false positive, true negative, false negative. Any questions on those concepts? Okay, so we're going to build from there. Can someone guess, just using these 4 terms that we just learned, what's an equation for the accuracy of a model, just based on your intuition of what accuracy means? Okay, so like in terms of TP, FP, FN, TN, what would that be?
TP plus TN all divided by TP plus TN plus FP plus FN.
Yep, exactly right. So let's write that out. So as our intuition might tell us, the accuracy are the true predictions. So that's the true positive plus the true negative. So everything the model got right divided by all of the data points, the number of data points in the data set, which is true positive plus true negative plus false positive plus false negative. So accuracy is great as a starting metric. Unfortunately, machine learning people really don't like accuracy alone because it has a few problems and it also doesn't tell us the full picture depending on what we're trying to look at. So to demonstrate one of the problems with accuracy, let's look at what is the accuracy here. And so I'm going to draw a table. This is maybe starting to look somewhat similar to the table you have in your homework, where you have your true value and predicted value. And let's say the true values are 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. And let's say we got really fancy and we wanted to build a machine learning model, and specifically a classifier, when we wrote the following Python code. So this input x. Let's even say it takes x1 and x2, so it's a 2-input model. Let's say we were super fancy and our classifier had the following code. So that means the predictions would be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Can someone tell me what the accuracy is in this case? According to our accuracy equation.
90%?
Yes. Does this intuitively seem like it should be 90% accuracy? No.
Kind of.
I mean, technically it is from the definition, but should this be 90% right, I guess, if accuracy is a proxy term for the correctness or performance of a model?
Sorry, is classifier the model here? Like the ML model?
Yeah.
Okay.
Yeah, I guess good question. So a classification model is called a classifier. Put that in parentheses. Yeah, so this would get accuracy to be 90%, even though the model didn't do anything. It's just predicting 0 every time. So for that reason, there are, and for other reasons, because we might want to know other properties of the model, there's a series of evaluation metrics that are common to use in machine learning and for classification models. Let's look at homework 1. Oh yeah, and you're asked to calculate some of these for question 3. So let's define those now. So one of those is called the precision metric. Sometimes this is also called the positive predictive value, depending on which field of research you're doing, basically. So the precision is defined as the true positives divided by the true positives plus the false positives. And intuitively, you can think of this as the correctly predicted positives divided by the total predicted positives. So out of everything that was predicted to be positive, what percentage of those data points that were predicted to be positive were correctly predicted to be positive? So the next metric is called recall. If you ever, want to publish a machine learning paper, you can't just put accuracy ever. So these are the metrics that you would always talk about when you're doing a machine learning evaluation, including for your final projects, by the way. Don't just report accuracy. So recall, also sometimes depending on your field of research, is called sensitivity as well, has the following equation. So it is the true positives, again, in the numerator, divided by the true positives plus the false negatives. And intuitively, you can think about that as the correctly, again, in the numerator, correctly positives divided by what are actually positive. So divided by the actual positives. So in precision, it's about out of the things that were predicted to be positive, what proportion were correctly predicted to be positive. And in recall, it's out of the things that are actually positive, what proportion were predicted to be positive. Couple more metrics, because these are just important to learn about in machine learning, because everyone uses them. Next is called specificity, and that has the following equation. So that's true negative divided by true negative plus false positive. And intuitively, that's the correctly predicted negatives divided by the actual negatives. Sometimes sensitivity and specificity go together because they're looking at the same thing, just one is looking at that for positives, the other is looking for that same thing but for the negatives.
Question?
Yeah.
Why is there no precision for the negatives?
Precision for the negatives. Great question. So our last metric, so notice how precision is called positive predicted value. We also have a negative predictive value, which is, as you said, the precision for negatives. I like that. So that would be true negative over true negative plus false negative. And we could basically take the intuition for precision and swap out positives with negatives. So correctly predicted negatives divided by the total number of predicted negatives. So in machine learning, it's really common to have a model that can have, for example, high precision and low recall. You can have a model with high recall, low precision, and it really depends on the type of application that you're doing as to which one you care about. So for example, in one scenario in healthcare, again, sorry, I talk a lot about healthcare, you might have a situation where you want a screening tool. So you're building a machine learning model that's really wants to find the positives or the cancers or whatever you're trying to detect. But if it misclassifies some of the people who don't have cancer as having cancer, it's not the end of the world. So in those situations, I mean, it could be in some situations, but for a screening tool, that's okay. So you really want to optimize in those situations for recall, but precision, if it suffers a little, it's okay. I mean, if ideally precision would be high too, but if recall's low, you can't use that model, at least as a screening tool. So that's just an example of why in different scenarios, different metrics matter. You should think, about situations where you might care about precision over recall. I'll leave that up to you and
Is there a
the exam.
scenario where we need all of them?
It's probably, yeah.
Question.
Yeah.
For question 2, it says to create an Euler curve. That's like does that mean we make a 3-dimensional curve?
We haven't gotten to ROC curves yet. So now basically you have the material to answer question 1 and 3 in the homework. So now we're about to get to question 2, but there's one other thing I want to cover before we get to question 2 material. That might end up being next class. So another common evaluation tool in classification models is called the confusion matrix, which kind of sounds like an interesting name, but it's not so interesting when you learn about it. So really what the confusion matrix is in the case of binary classification, you draw a grid like this, and over here you put the number of true negatives, here you put the number of true positives, here you put the number of false positives, here you put the number of false negatives. In other words, predicted value, true value, 0, 1, 0, 1. So when you get 0 and 0, true negative, 1 and 1, true positive, etc. This could also generalize to multi-classification, where you can have 1, 2, 3, 4. You can have the predicted values and true values, 0, 1, 2, 3, 0, 1, 2, 3, and do the same thing. How many true values that are 2 were predicted to be 1, that would go in there, etc. And a nice, good, perfect confusion matrix would have really high values here and zeros everywhere else. So when you see these confusion matrices in research papers, you're looking for the diagonal to have high values. You don't care elsewhere. Just something to be aware about because it shows up a lot in other situations. So I now want to talk about 2 ways that the ideas of precision and recall and the other metrics we learned about can extend to multi-class classification. I know we haven't covered how multi-class classification models work, but that's fine. We will cover that soon. Basically, all you need to know is that instead of predicting 0 and 1, you can predict 0, 1, 2, 3, etc. for multi-classes, and there are, and the rest of the details don't matter for today, but we will get to there. So in multi-class classification, there are a couple ways to make these traditionally binary metrics extend. let's look at an example. So let's say we're doing a three-way classification problem. And we have, I'm going to switch up the order of things. I hope that's okay. So we have y can be 0, 1, 2. Y hat can be 0, 1, 2. It's kind of arbitrary whether you draw y hat on this side or on this side. And let's say that our model performs as follows. So I need to draw myself a little more room here. So this first example is going to be a technique called macro averaging. So what you do in macro averaging is first you calculate the each metric individually for each class. So let's say we first calculate the precision for class 0, and in that case that would be 8 over 8 plus 10 plus 1. We can do the same for precision for class 1, so that would be 60 over 5 plus 60 plus 50, and precision for class 2 would be 200 over 3 plus 30 plus 200. And yeah, I won't do them all for recall, but just so you can see 1, recall 0 would be 8 and now we go through the columns. So 8 plus 5 plus 3. Essentially, you're looking at your class versus every other class, rather than your class versus not your class, etc. So to calculate the overall precision using macro averaging, would be precision 0 plus precision for class 1 plus precision for class 2 divided by 3, which in this case would give us 0.60. The other way you can extend these metrics to multi-class classification would be micro averaging.
Can you scroll up just a little bit?
Yeah. Where we want to make a what's called a pooled confusion matrix, where we basically where we collapse what we care about into
Hey, just go up. Sorry, I'm just trying to get the numbers fine. Okay.
okay,
Thank you.
into the following, where we look at how many times was the true value what we're interested in, and how many times was the true value not what we're interested in. And the same thing, how many times was the predicted value what we're the class we're interested in, and how many times was it not the class we're interested in. As an example, that would be for here we would put 268 because the number of times where the predicted value was the same as the true value was 200 plus 60 plus 8. So maybe in parentheses equals 200 plus 60 plus 8. And doing the same thing for the other places. And then once we've collapsed it like this, so we're just looking at how many times was what we're predicting matching the true thing, and how many times was what we're predicting not matching, how many times was, etc. Then we could just calculate precision in the binary way now that we've pooled the confusion matrix. So now in this case, the overall precision would be equal to 268, and now we're just using our original definition of precision for binary variables. So 268 over 268 plus 99, which gives us 0.73. So notice that depending on whether you're using macro averaging or micro averaging, you're going to get a pretty different results. Usually people prefer macro averaging because in micro averaging, you'll notice that whatever class happens to have more examples tends to sway the decision or pull the decision because you're collapsing everything. So in practice, people like macro averaging because micro sways the result towards the majority class, or the class that's represented more in the data set. We have 2 minutes. I want to pause and see if there's any questions. Yeah.
Are the 299s in that pool grid the same number, just repeated twice, or are they obtained different ways?
They're obtained in different ways. So the top one is the number of times where when the predicted value was one thing and what the true value was not that thing. And whereas in the bottom, it's where the true value the true value was one thing and the predicted value was not that thing. So they're kind of reverse. So for to make it specific, so in this top right corner for this 99, it would be from summing up let's draw this up here. This would be from summing up 11 plus 55 plus 33. And this 99 would be from summing up 8 plus 40 plus 51. I'll let you figure out where those numbers came from.
What about the very final?
Sorry?
What about the final number? You just add everything in the matrix.
The final number?
635.
Yeah. So this is, no, this final number is the number of times where the predicted value was not the corresponding value of interest. So yeah, it would be 340 plus 212 plus 83.
How did you get 340?
I'll leave that to you for next time, or we can cover it at the beginning of class next time too. Either way, because we're ahead. So I think next time we can cover that, and then we'll cover how to do question 2. And I think we'll be in a good place by the end of this week for homework 1. Okay, I can't stay for question